Okay, so sorry for waiting so long. I'm Jiyuan Zhang, third-year PhD student from Tsinghua University, by Shudong. And today I'm going to present my recent work, our recent work on speeding up VBBinaryLensing and VBMicroLensing through compiling and algorithmic optimization. And this is work of collaboration. My collaborators are Shudong, Valerio, and Vito. So before starting, I need to give you the contents or to say the summary of this talk. So we use compiling optimization, that is inlining all the complex operations, and the algorithmic optimization, that is convert our n-square algorithm to a log n. And finally, we achieve more than 3 times speed up at all magnification ranges shown here. You see all the blue points are above the 3. And I'm going to first introduce the method to calculate finite source magnification. Let's start from the binary equation. The GS is the source coordinates, while Z is the image coordinates. And there are basically 2 methods. First is continuous integration, and second is inverse reshooting. For continuous integration, you need to sample alongside the source contour. So the GS is given, and you need to calculate the Z. And after Z is solved out, you need to connect all the image positions to form consecutive image contours. And the magnification is just the image error divided by the source error. But the inverse reshooting is kind of a reverse process to the continuous integration. In continuous integration, the GS is given and you need to solve Z. But in inverse reshooting, the Z is given and you need to calculate the GS. So you can shoot from this uniform image plane to the source plane according to this equation, and you'll find that there are some specific parties. It's just the cosine. And we can place the source contour here, count how many rays are located within the source contour, and the magnification is just proportional to that. And today I'm going to mainly talk about the optimization of continuous integration, especially for the widely used VBBinaryLensing and recently published VBMicroLensing. So to speed up VBMicroLensing, we first profile it with Intel V2 profiler to find which part of the code is bottleneck. And this panel shows the time used by each function. We found that the most time-consuming functions are the complex multiplication and addition. And we can also check time used by each line of the source code. For example, this complex multiplication function consists of 3 lines of source code: calling, computing, and returning. We find that calling and returning cost comparable time to computing, which means that this function is totally not inline. It causes large overhead. So we inline all these complex operations, and you see after inlining, there is no complex operations here, and we go back to the complex multiplication, and we found that there is no calling and returning time, and only calculation cost time. So this function has already been inlined into these higher level functions. So what's the speed up through inlining all the complex operations? And hereafter we'll name it as compiling optimization. We use VBMicroLensing to calculate magnification from 1 to 1000. And here is the CPU time in seconds for each point. And the black points are for the version with no optimization, and the red one is for version with compiling optimization. So by the way, the compiling optimization has already been incorporated into VBMicroLensing version 4.1. And this panel shows the speed up, which is just defined as the black point time divided by the red point time. And we notice that there is more than 3 times speed up at low magnification, but the speed up drops as magnification increases. And there is only a 1.4 times speed up at magnification 1000. So why is that case? To answer this, we need to first look into the 2 steps in continuous integration. First, we need to solve length equation to get image positions. Second, we need to order this image to form consecutive image contours. So we measure the time used by these 2 steps separately, shown in this figure. And the blue points is for solving length equation, and the red points for ordering images. We found that solving length equation is about 10 times slower than ordering images at low magnification. But the ordering images grows much faster, and it's about 3 times slower than solving length equation at magnification around 1000. So this can naturally explain the previous question, why speed up drops as magnification increases. Because inlining complex operations mainly works on solving length equation, but solving length equation is not the most time-consuming part at high magnification, so we do not expect too much speed up from just optimize the solving length equation. And that leads to another question: is that why the ordering images, these red points, grow so fast than the blue points? The answer, I will give the answer in once, because if you consider the time complexity, solving length equation is the ON algorithm, while ordering images is the ON square algorithm. And N is the number of points on source contour, and higher magnification means larger N. And it's easy to understand that why solving this equation is the ON one, because you have n points alongside the source contour, and you need to solve n-less equation is just the time is just proportional to n. And we will give you the answer why it's the ON square one for all the images in next slide. So with n increases, the n square grows much faster than ON. That's why the all the images grows much faster. And to understand why all the images is the ON square one, and can we do it better like in n log n? So we need to first understand how all the images works. So for triple case, we can have, for example, 4 image contours, and each contour can consist n points starting from theta equals 0 to theta equals 2 pi, and assume that this interval theta 1 to theta 2 has the largest error. So we are going to insert a new set of images to this interval with the theta nu is the median of these two nodes. And to insert this new set of images, we need to first divide between the theta 1 and theta 2, and second, reconnect the closest image pairs. And you notice that shuffle happens here because the original Z1 contour is not connected to the original Z1 contour. Instead, it's connected to the original Z2 contour because this pair has the smallest distance among these 4. And this pair also has the smallest distance among these 4. So shuffle happens here, and that's the reason why VBMicroLensing uses sorted linked list for image contours, because it's easy to divide and reconnect. But that leads to another question, is that how to find between which nodes or which pointers we to do the division. And that's an equivalent question to how to find where to insert 13.5 in this below sorted linked list. So we need to look through the linked list to compare. We found that 3 is smaller than 13.5, then we go to the next node, and 4 is smaller, then we go to the next one, until that we found 14 is larger, then we know that we inserted in these 2 nodes. And as it's ON to find 1, there's its ON square to find n position. That's why all the images ON square algorithm. And you may ask me why we cannot do binary search. Like we first go to the midpoint, and then we go to the cross section point, and that will lead to a log algorithm. The reason is that only array can do binary search, because array has the ability to do random indexing. But linked list does not have the ability to do random indexing, so it can only loop through it to find a position. But we have another data structure called a skip list. Skip list is very similar to the linked list, but it may have multiple levels of pointers. For example, this node 12 has 3 levels of pointers. The third level pointer points to the next node, and this node points to a skip 1 node, and this skips 3 nodes. So if we want to insert 13.5 in this skip list, we first go from the header, and then we go to the 12, we find 12 is smaller than. So we go to this one and find it's a non-pointer, then we go back and go to the next level, and go to the 14, find it's larger, then we go back, go to the next level, and we go to the 13, it's smaller, and go to 14, it's larger. So we know we will insert it in these 2 nodes. So you see, it's a log algorithm to find 1. There's a log to find n positions. So we achieve our original goal. And to better understand the magic of skip list, there is a great similarity between the skip list and the subway system. For example, a subway system may contain a local line which stops every station, and we also contain an express line that stops only at some stations. So if you want to go to a far away place like this station, it's better for you to first take the express line, and at some place you transfer to the local line and finally get to your destination. So the idea behind the skip list and the subway system is basically the same. It's just to skip some nodes or skip some stations. And another n-square algorithm is finding the interval with largest error. So previously we have already showed the image contours, but now we go back to the source contour, starting from theta equals 0 to 2 pi. And in each interval, we will have an error of this interval. And we need to find the largest, we need to find the interval with largest error and to insert a new point in between this interval. And 2 errors are updated. And again, we need to find the new largest error. So we need to find the largest error, we need to loop through all these errors, and it's an ON algorithm, and we need to add n points, so we need to loop through n times. It's another n-square algorithm. And at the same time, we need to calculate the total error. The aim is to stop adding points if the total error is already smaller than the threshold. So, but we must convert all the n-square algorithm to log n. So how do we do that? We divide a new data structure, it's called augmented priority queue. and it consists of two parts. First is the heap, and second is the sum tree. And the two trees are correlated through the index attribute of the first part. And for the root nodes, this root can always start the interval with largest error, and this root always start the total error. So it's very easy to access to them. And if you insert a new point, for the left part, you only need to swap with the parent nodes if the parent is smaller than the current one. And for the right part, you only need to add the current error to always parent to the root node. So the data structure property can be maintained within log after inserting or deleting one point, because the layer is layer is just log, and thus is unlog for endpoints. And I want to note that the right part seems to be complicated, but it's for consideration of avoiding numerical noise, especially for avoiding two large numbers reduction. You know, the two large number reduction can cause the accuracy degrade a lot. And with the help of the red part, even if some nodes is deleted, there is no reduction performed. And finally, we get to the result part. So what's the speed up through converting all the n squared to a log? And hereafter, we name it as algorithmic optimization. And we compare the performance with only compiling optimization and the compiling plus algorithm optimization. And the speed up, you see, it increases as magnification increases. And it's about 1.5 times speed up at magnification around 200 and 3 times speed up at magnification around 1000. And it's easy to understand that why speed up increases as magnification increases, because speed up is just proportional to the n squared divided by n log n. So it's this value, and as n increases, this value just increases. Okay. And okay, so now we can combine the compiling and algorithmic optimization together, and we can find that there is more than 3 times speed up at all magnification ranges. And I'm especially happy about this lift. And another issue is that why the VBBL will enjoy these optimizations. The answer is that VBBL will also enjoy the algorithmic optimization, because the VBMicroLensing and VBBL use similar algorithm to find the largest error or to order an image. So you see that here is the result for VBBinaryLensing, and the speed up is also around 2.5 times at 1000. But for the compiling optimization, it's kind of tricky because it depends on the compiler. Some compiler already inline all the complex operations, but some compiler will not. So I will suggest you use the newest version. And the last one is the speed up through algorithmic optimization. It actually depends on the relative tolerance, which is the relative precision goal we set. And I want to note that all previous results are based on the relative tolerance equals 10 to minus 4. Because next generation space telescopes may have 10 to minus 3 relative precision, photometry precision, and our numerical results need to be at least an order of magnitude more accurate than the photometry. So we set the relative tolerance to 10 to minus 4 as a practical threshold. And if you set it to a more demanding relative tolerance, like 10 to minus 5, the speed up will further increase. You can see that for 10 to minus 4, it's about 3 times, and for 10 to minus 5, it's about 6 times faster, because n is larger, and the speed up is just basically proportional to n. Okay, here's my summary part. I'm not going to read through it, but I'd like to note that all the code has been uploaded to my GitHub repo, fast VBLensing. And if you can take a picture of this summary page and start this repo and test the code's performance, I'll be especially happy about that. I'm also discussing with Valerio about updating all this optimization into future version of VBMicroLensing. So that's all. Thank you.
Question about the compiler optimization.
Yeah.
Why is it that some compilers don't do this?
I have no idea.
You have an idea?
I basically use GCC and G++, but if I do not add inline before my function, it will just not inline. But Valerio use MSVC, and that compiler will inline without inline keywords, so it's different. But that's for the VBL. But for VBMicroLensing, it's another story. So the original version of VBMicroLensing, all complex operations are put to a separate function, a separate file. And you know that if you have multiple files, it will be compiled separately. So other files which use this complex operations does not know what this function is truly is. So even if MSVC, it cannot inline this function. So finally, Valerio put all the things into a single file, and things are good now. Yeah.
We have time for a very quick question with Wei-Ching.
Okay, Jiyuan, okay, I have a question for you. Why is your effective 3, effective 4 improvement important? Why?
I think at magnification 1000, the improvement is just beautiful, but not that real useful. But I think the improvement at magnification 200 or 300, that's more meaningful because there are a lot of magnification, high magnification events will reach this region, but there are very rare events will reach the magnification 1000. So I will say that 1.5 times scale or 2 times scale is more practical value.